Wait another couple of minutes, Kong, and then we can get started. Yeah.
Okay, boss.
Yeah. Yeah. 11:05.
I'm not used to being late, Bob.
Well, 11:05 is when we start class at MIT. And 10:05, 11:05, 9:05.
In this country, yes.
Yeah. You're not late. You're on time.
Okay, okay. Someone raise hand.
Yeah, so Bob, if classes start at 11:05, when do the students think they can leave if you're late?
The class ends at 11:55.
Whether you're there or not.
Right. So you get a 10-minute break between classes, okay?
You know, the joke about the students who are attending a class with a visiting German professor, and the class goes on and on week after week, and the students are gradually dropping out. A student says one day, "Herr Professor, when will the class end? And the professor says, the class ends when there's only 2 of us left. So the day finally comes where only 1 student shows up, and the student says, Herr Professor, there's only 2 of us. Is the class over? And the professor says, no, God is always with us. That makes 3.
Okay. All right, Con, go ahead. It's 11:05.
Yeah, it's 11:05. All right. Good morning, good afternoon, good evening, everyone. It's good to see you all again, and welcome to our Zoom session. So before we begin and pass the session to Bob to introduce the speakers, I will just do a quick update or briefing that I usually do prior to the speaking session, the talk. All right, so you can all see my screen. So as usual, the thing I will ask you to do is always like subscribe to the mailing list. My technical support, Michael Madini, will actually like copy and paste the link, or I will do it like into the chat room. So if you have not done so, feel free to subscribe to it so that any other announcements of the future events, or if there's a change of date or change of time when the semester begins, we will let you know. And if you're interested in listening to the previous recordings of the recordings of previous talks, they can be found on our group website, which is here. And if this is your first time here, if you want to ask questions, you can type your questions like anytime, like during the talk. But I would like to ask you to type your questions in the Q&A session, in the Q&A feature that you can see at the bottom of your Zoom window. And not only you can ask questions, you can also comment on it. You can also vote it so that those questions with the most number of votes will be asked first. And also, like, do not type your questions in the chat. You can use chat to chat, say hi, but don't type your questions there because like it will not be delivered to the speaker. And last, so all the Q&A questions of the past talk of previous talks will be they are actually recorded, and and I will upload it to the Dropbox. So even though after the talk, you can still have a follow-up discussion, and if you're interested, you can look at like some of the answers typed by the speakers. If we are not able to answer all the questions by the first speaker, you can just look it up and comment and do whatever you want. So everyone has access to it. So it's on the Dropbox. It's also like everything is everything that I said here can be found on our group website. All right, I will now stop sharing my screen and I will pass the session to our Bob Griffin so that he can introduce our speakers today.
Okay, so today we have 2 excellent speakers again. One from Japan, all the way from Japan, Hiroki Nagashima, who will be talking to us about some solid state experiments that he developed when he was a PhD student in Lille, at the Olivier Lafon and company. And the second talk will be from Gail de Pape, who is in Grenoble, France, on low temperature magic angle spinning, among other things. So Hiroki, you want to get us started? Start showing your slides.
Okay, can I start?
Yes, we can see your slides, okay?
Okay, so thank you for introducing me. My name is Hiroki Nagashima. So I talk about methodology development for observation low gamma quadrupolar nuclei by surface-enhanced NMR spectroscopy. I am a research scientist in AIST, Japan. AIST is the National Institute of Advanced Industrial Science and Technology, located in Tsukuba Science City. So, Bruker 400 MHz mass DNP system was installed in 2017 in AIST. I am managing this system and studying methodology development and application of mass DNP for material science. I start the introduction of DNP Surface-Enhanced NMR. In current mass DNP experiments, there are 2 approaches, direct and indirect. So in case of direct DNP, electron polarization can be transferred to target nuclei directly. On the other hand, in case of indirect DNP, the polarization is transferred to target nuclei via proton-proton spin diffusion and then by cross-polarization. In this presentation, I focus on the polarization transfer proton to quadrupolar nuclei for indirect DNP approach. Sometimes our target is half-integral quadrupolar nuclei. However, in this case, the problem is spin lock under CP mass. So CT selective spin lock need very weak RF field. This condition should avoid R cube dip condition and lead to RF offset sensitive. Moreover, simultaneous spin lock is of different CQ site is difficult. So CP mass experiment is not robust and lead to spectral distortion and need long optimization in advance. So we need other polarization transfer methods for quadrupolar nuclei. So Presto 3 transfer is an alternative approach of CP mass. So Presto 3 can perform polarization transfer by applying R symmetry-based recoupling to proton channel. The advantage of Presto is no spin lock on quadrupolar nuclei, and CT selective pulse is only applied to quadrupolar nuclei. This leads to robust experiment and easy to set up the condition using test sample in advance. So Presto method was introduced to indirect DNP experiment in 2015 by Dr. Peras and Dr. Prusky. And Presto has advantage of sensitivity and not spectral distortion compared to CP mass. So the DNP is an alternative approach. DNP is a method of choice for polarization transfer for quadrupolar nuclei. DNP is similar to Presto but use different R symmetry coupling such as SR4. So advantage is also no spin lock on quadrupolar nuclei. But I want to point out that this advantage of both sequence may be signal reduction due to proton-proton dipolar coupling, especially at slow spinning speed using 3.2 mm LT mass probe and at low temperature. At this point, I show you the simulation result of robustness to proton-proton dipolar coupling. So DNP condition is assumed to 7 kHz proton-proton dipolar coupling. So blue line is Presto and the black line is DNP. So this left figure shows the case of large heteronuclear dipolar coupling, so such as proton to aluminum. So in this case, DNP show poor proton-proton dipolar decoupling performance. On the other hand, Presto show good performance. However, in small heteronuclear dipolar coupling system, Presto also poor proton-proton dipolar decoupling performance at DNP measurement condition. This means that it is difficult to perform polarization transfer for long distance under our low gamma quadrupolar nuclei by Presto transfer. So we want to improve recoupling sequence. In case of Presto, R symmetry-based recoupling such as R1825 is used. This recoupling has a single quantum Hamiltonian, which read gamma encoded and not robust to CSA, and the dipolar truncated, which means non-long range transfer in abundant nuclei. As we checked in previous slide, so proton-proton decoupling performance is not enough for observing a low gamma quadrupolar nuclei. I try to improve the performance by using window R element and composite R element. However, it is not improved significantly. So place is almost optimized at present. In case of DR inept, so R symmetry coupling such as SR4 is used. This recoupling has longitudinal two-spin order Hamiltonian, which leads to robust offset CSA and RF inhomogeneity and higher scaling factor, and not dipolar truncated, which means long range transfer is possible in abundant nuclei. But very poor proton-proton dipolar decoupling performance under slow spinning speed. So we also try to improve this proton-proton dipolar decoupling performance for DR inept sequence. The idea is to use adiabatic symmetry-based recoupling. So a typical rectangular R element can be changed to frequency and amplitude modulation shape. This sine-cosine modulation recoupling have been called sperm recoupling. Recently, we found that sine-cosine shape can be changed to tan-tan shape, which is more robust to anisotropic interaction. They have been used as short high-power adiabatic inversion pulse. We check the robustness to proton-proton dipolar coupling for transfer efficiency. So this adiabatic recoupling significantly improves the dipolar robustness to dipolar coupling, and we found that tan shape is the best R element. Finally, supercycle can be combined to tan R element. However, for this recoupling, one disadvantage, high RF power demand, but no problem for our 3.2 millimeter DNP probe. So we can combine this decoupling to DR inept sequence. In addition, we further improve the DR inept sequence. In case of DR inept, whole sequence must be rotor synchronized, and especially beginning of recouplings must be rotor synchronized due to non-gamma encoded property. So these delays between recouplings are necessary due to finite pi half and pi pulse length. Here, I noticed that proton-proton dipolar coupling reduces the signal during the delays. So it is necessary to suppress signal losses during the delays. For these issues, I came up with the idea to insert CW irradiation into these delays. If CW irradiation has high RF phase and short duration, so CW decoupled dipolar proton-proton dipolar coupling completely. So we check the robustness of proton-proton dipolar coupling, and so CW irradiation version significantly improves the transfer efficiency compared to without CW version. So CW irradiation suppress signal losses during the delays. So again, I show the simulation result of the robustness to proton-proton dipolar coupling. So new DR inept outperform pressed transfer in case of small heteronuclear dipolar coupling system and achieve 85% of maximum efficiency for small heteronuclear dipolar coupling. This means that we can perform indirect DNP experiment for low gamma quadrupolar nuclei very efficiently. So in addition, there are other advantages of new DR inept. So at first, higher scaling factor. High scaling factor minimizes T2 prime losses during recoupling sequence. And robust to RF inhomogeneity, this simply improves the efficiency. And robust to RF offset and CSA. These properties are preferable for DNP experiment in higher magnetic field. From next, I show DNP experimental result of new DR inept. At first, I showed the case of large heteronuclear dipolar coupling system. I selected aluminum-27 of gamma alumina and oxygen-17 of magnesium hydroxide. So gamma alumina is widely used in industry as a catalyst and catalyst support because of large surface area and unique acid-base property. And aluminum-27 is a sensitive quadrupolar nuclei because of moderate Raman frequency and 100 natural abundance. So left figure shows a comparison of new DR inept and conventional DR inept. So new DR inept got the sensitivity gain about 16 compared to conventional one. So this is a great improvement. The right figure shows the comparison of new DR inept, Presto, and CP mass. For the CP mass, it is possible to optimize Hartmann condition for this system because of high sensitivity and moderate CQ. However, long optimization is necessary in advance. From this result, new DR inept is twice more efficient than Presto. So new DR inept has already advantage in the case of large heteronuclear dipolar coupling system. And frequently, magnesium hydroxide is tested by indirect DNP experiment. In this case, heteronuclear dipolar coupling is very large due to short distance. So from this spectrum, the spectral shape of new DR inept is similar to ideal simulation spectral shape. On the other hand, Presto exhibits spectral distortion due to relative orientation between quadrupolar interaction and heteronuclear dipolar coupling tensor. So another advantage of new DR inept is to provide less spectral distortion. So from next, I show you the result of small heteronuclear dipolar coupling system. So all target nuclei is low gamma quadrupolar nuclei. And the QCP image acquisition was applied after DR inept transfer. And the sample gamma alumina, molybdenum O3 titanium O2, and aluminum doped ZNO nanoparticle. At first, unprotonated oxygen site has a small heteronuclear dipolar coupling and difficult to acquire the signal by indirect DNP experiment at natural abundance. So in the left figure, I compared the transfer efficiency among new DR inept pressed direct DNP. In these spectra, new DR inept is 4 times more efficient pressed transfer. The time saving is about 16. Also, new DR inept is about 7 times more efficient than direct DNP. However, this field of position is proton. So the signal of direct DNP is doubled in case of oxygen-17 optimal field position. However, new DR inept remains 3.5 times more efficient than direct DNP. So these gains are great advantage to observe unprotonated oxygen 17 on the surface. Another advantage of new DR inept is to observe OH group and unprotonated oxygen sites separately by changing recoupling time. So recoupling time of OH group and unprotonated oxygen site is very different. In addition, T2 prime of OH group is very short due to large heteronuclear dipolar coupling. So the signal of OH group is completely decayed after 1 millisecond recoupling time. So thanks to this property, we can clearly assign the OH group and unprotonated oxygen sites separately. This analysis can be applied to other material. So we analyze the surface structure of molybdenum-03 titanium-02. So molybdenum-03 titanium-02 is widely used heterogeneous catalyst, for example, oxidation of hydrocarbon and alcohol, and aterification of alcohol, and hydrodesulfuration in petroleum chemistry. So similar to previous analysis, we observed unprotonated oxygen 17 spectra and OH group separately. From unprotonated oxygen site, we observed oxymolybdate cluster. On the other hand, from OH group, so we observed strong boron acid site. This is expected to be originated from oxymolybdate cluster. This structure plays an important role in catalytic activity for above reactions. We apply the method to detect molybdenum-95 or molybdenum-03 titanium-02. This is the first observation for the surface molybdenum-95 NMR spectrum by indirect DNP experiment. So left figures, the sensitivity of new DR inept is higher than that of 5.5 times higher than that of Presto. So this is a great advantage for observing low gamma quadrupolar nuclei. In the right figures, we can compare surface and bulk spectrum. So alpha molybdenum-03 indicates only 6 coordinated molybdenum sites. On the other hand, molybdenum-03 titanium-02 indicates 6 coordinated and lower coordinated molybdenum sites. And moreover, surface indicates significantly broader compared to bulk. This means that surface have more disordered structure compared to bulk structure. So new DR inept is successfully applied to titanium nuclei of molybdenum-03 titanium-02. This is the first observation for the surface titanium NMR spectrum by indirect DNP experiment. We can compare surface and bulk spectrum. The surface spectrum shows significantly broader compared to bulk. So surface has more disordered structure. And the surface spectrum indicates large amorphous fraction and additional surface components such as bonded to OH and bonded to molybdenum. So this structure may affect the formation of molybdenum oxide and oxymolybdate cluster. So new DR inept provide new insight into the surface structure of catalytic support, including low gamma quadrupolar nuclei. Finally, we try to detect zinc 67 surface spectrum, so aluminum-doped ZNO nanoparticles. So aluminum-doped ZNO nanoparticle is a promising alternatives in indium tin oxide as optically transparent electrode application. So indium is a rare metal. This means high cost and concerned about stable supply. So aluminum-doped ZNO is show good electrical conductivity and very cheap materials. These are promising property. Also, this is the first observation for the surface zinc 67 NMR spectrum by indirect DNP experiment. So compared to typical ZNO particle, so aluminum-doped ZNO nanoparticle have disordered structure. And the surface spectrum indicates the presence of ZN aluminum-2O4 byproduct. This is not observed on the bulk spectrum. So this byproduct is only located on the surface. And I point out this ZN aluminum-2O4 byproduct does not cover all the surface as we observe large ZNO resonance. Additionally, we were able to observe oxygen-17 and aluminum-27 of aluminum-doped ZNO nanoparticle by NUDR inept sequence. We observed alpha aluminum-2O3, ZNO aluminum-2O4, as well as ZNO phase for oxygen-17 spectrum. This is complemented with aluminum-27 DNP NMR spectrum. So aluminum-27 spectrum indicates alpha aluminum-2O3 and ZN aluminum-2O4. So in conclusion, in addition to ZNO phase, alpha aluminum-2O3 and ZN aluminum-2O4 exist on the surface. So these insulating shells decrease electrical conductivity. This is a key structure to improve electrical conductivity of these materials as opto-transparent electrode application. So finally, I concluded that NUDR inept is easy to set up and much less spectral distortion and very efficient, especially for low gamma quadrupolar nuclei. Compared to pressed sequence, the gain is 4.0 in case of oxygen-17 and 5.5 in case of molybdenum-95. The time saving is about 16 and 13 respectively. The tuning of LT-mass probe can be extended down to tungsten. So NUDR inept can be applied a variety of half-indical quadrupolar nuclei, and it would be useful for a variety of research fields in the future. So this research is supported by NEDO project, and the sample is provided by AIST. And this research is a collaboration with UCCS in Lille University and the CNRS France. And I would like to thank Jean-Paul, Olivier, and Julien. I'd like to thank Bruker for supporting the DNP experiment. Finally, thank you for your attention.
Okay, thank you, Hiroki, for your interesting presentation. And also, it's nice to show that there's something that's more promising than Presto, which I've not used Presto, but I heard like that's what people call like the gold standard of the sequence of using this. So let me just go to the Q&A. I don't want to ask a question because there are quite a lot of them from the audience. So first question from Fred Perras. Have you tried using R elements that are only phase modulated and not amplitude modulated? And he's thinking that the delays are introduced in between the hyperbolic tangent pulses due to their tapering could also lead to the decay.
So the question is this one? So
the first one with 5 volts. Yeah, first one.
First one. So sorry, can I see the sentence?
Open the Q&A.
Q&A.
Yeah. It's at the bottom of the Zoom window. You can see the Q&A.
Phase modulated.
Or maybe like Olivier,
yeah,
you like.
But I have tried well, phase modulated and amplitude modulation. So it's both, I think.
Yes, we don't try just phase modulated pulse. It could be a good idea. No, if the amplitude modulation lead to losses due to the proton-proton coupling. It's a good question. We need to try. I don't know, Hiroki, if you have tried. Oh.
I have tried one time only the phase modulation, but not so different. So
okay,
this version are only phase modulation, not different.
Okay, now let's go to the next question. We have quite a lot of them. Can you comment why SR4 avoids dipole truncation but not R18?
So this is due to so Hamiltonian shape. So SR4 is a longitudinal two-spin order Hamiltonian. This commute itself Hamiltonian, and but Presto single quantum Hamiltonian. So this cannot commute itself Hamiltonian.
Okay, next question from Henry. Henry, could you explain the gamma encoder 30% increase signal on slide 8? Is it something general or something also experimentally? Is it for all or just for this special case of SR18? Can you go to slide 8?
Okay, so is it something? This is general. So sometimes we observe more signal, but for real experimental conditions, so CSA, there is a CSA. So Presto is not robust to CSA. So the sensitivity decrease due to CSA. So sometimes not good sensitivity for so also gamma encoded, but 30% increase signal on experiment is not observed due to CSA.
Okay, so like next question from Anonymous. How does the DR in depth sequence that you show here compare to all other sequences they have shown like CP, Presto? I think you show like a gain of 4 or 5.5 at room temperature. That is for non-DNP situations. Are the gains still the same at room temperature?
Room temperature. I don't know. This is possible for so comparison at room temperature. Yes, this is so we can compare so these sequence at room temperature. So it's normal.
So yeah, there is no difference.
Yeah, no difference. But just situation is different. So in DNP experiments, there is a solvent in the sample, but for room temperature experiments, so no solvent. So for example, proton-proton dipole coupling is strength is different.
Okay, so I was assume the answer is like, yeah, the gain are the same, whether you do it at room temperature or at 100 Kelvin for DNPs. All right. So I'm just trying to get more questions. So next question from David, were the materials oxygen-70 enriched or is it at natural abundance? Yeah, natural abundance, right?
Yeah, it's a natural abundance.
Okay, yes. And next, when comparing the DR in-depth to Presto on slide 15, do you see any dependence of polarization transfer on CQ?
Slide. Well, I don't. I didn't check detail, but I think no dependence of CQ for and the polarization transfer for DR inept and Presto. Yeah.
Yeah, it's the same because the sequence on the quadrupolar is the same.
CT selective pulse is only applied to quadrupolar nuclei, so I think not different.
Okay, so like next question, like it's an interesting one because like I also have this question in mind. When you're using these symmetry-based sequences, like, and is there any limitation on the large bandwidth? Or I'm just curious, like for example, like if you were to, I think you use like 100 kilohertz for the spinning frequency that you're using, like 10 kilohertz or something. If you were to spin faster, would you, what kind of other sequences would you use? You know, because like for the proton-proton coupling, you can perhaps like suppress it when you spin faster, you know, like maybe like 40 or 65 or something like that. So what would you envision in that case?
Okay, so question is this? So high mass frequency, so this adiabatic recoupling is the advantage is small for high mass frequency because of so I see, and so we need a very high RF field for mass frequency, high mass frequency for this adiabatic pulse. So it's difficult to apply high mass frequency, but the advantage is up to 40 kilohertz mass frequency for this pulse. I tried to simulate the efficiency for this recoupling. So I got the advantage up to 40 kilohertz, but 60 kilohertz is a less advantage. So similar to SR4, normal SR4 recoupling is similar to this pulse.
Okay. All right. So due to time constraint, I will only like just take the last question. So what's the difference between SR4 and R18 in terms of the symmetry selection or symmetry-based selection rules? Do they like recouple the same terms? In terms of the space and spin signature, or you can comment on the scaling factor if you want, or other stuff.
Symmetry selection, yes, so M equal, so yeah, both heteronuclear dipole recoupling and this R1825 also have proton-proton dipole decoupling. So SR4 is proton-proton dipole decoupling. So yes, M equals to also. Yes, normally it's symmetry selection is similar, but Hamiltonian shape is different, I think.
Okay, I think like is this like discussed in the paper? If it is, like then
maybe
all the
just
like,
I can complete. So SR4 is as Hiroki said before, longitudinal to spin order, IZ, SZ. R18 is and it's not gamma encoded. R18 is gamma encoded, and the Hamiltonian is the form E plus SZ, for instance, because it's a single quantum term.
Yeah. So property is very different between these sequences.
Oh, okay. Yep. So thank you very much for the Q&A. And then like I will now pass the session to Bob so that he can introduce our next speaker. Thank you very much, Hiroki.
Okay, thank you.
Yes, thank you, Hiroki. Yeah, it's a very nice presentation. Yeah. So our next speaker is Gail DePape. And Gail was a PhD student in Lyon, and he came